Hello and welcome to Samsung. In this video, I want to talk about the RF parameters and what needs, how and understand how the radio resource management works in case of the Samsung controllers. I will briefly touch upon high-level concepts that will help us understand how these parameters need to be tweaked. Now, for the most part, if you're doing a deployment in an SMB kind of an environment where it's a data only and there's not much going on, not much going on with voice, you may be better off leaving most of these parameters to default. However, if you are in an enterprise kind of an environment, highly dense environment, then it would be necessary to tweak certain of these, to tweak these parameters to obtain optimal coverage and optimal capacity. So it is very important that we understand some basic concepts. Now here, my assumption is that some of you are familiar with some of the RF concepts. And from this video's perspective, from the training perspective, I just want to touch upon what configuration is needed on the controller, what kind of hooks the controller provides when it comes to the radio parameters, and and how we can change those. All right, so that being said, let's get started. So in the controller itself, there are many areas where you change the radio parameters. For the most part, the global parameters are in configuration and the radio. So you can see 802.11an and AC, that's for the 5 gigahertz, and then you have BGN, that's for the 2.4 gigahertz radio. So let's come to 802.11an and AC. You have to make sure that the service is enabled. It's enabled by default. Here are some general parameters. As you can see, for the most part, everything is kind of grayed out. Here, I don't expect you to change anything except whether you want to select a bandwidth of 20 megahertz or 40 megahertz. Now, this is at a global level. There are parameters now which are available at an AP group level, which I've already discussed when I was talking about AP groups, where you can now apply the bandwidth setting on the AP group level. So now, since we are on the topic of bandwidth, let's talk a little bit about 20 megahertz versus 40 megahertz versus 80 megahertz. So if you are not already familiar with this graph, this is the channel allocation for 802.11 AC, uh, specifically on the 5 gigahertz, and it's also applicable on for 802.11n. So as you can see, these are the different channels that are available to us. Of this, you have channels in the Uni 1 band, which is 36, 40, 44, and 48, and in the Uni 3 band, 149, and then the ISM band, so 149 through 165. These are the most commonly used channels. And if I select a channel width of 20 megahertz, and if I just use Uni 1 and Uni 3, and ISM, I get a total of 4 here and then 4 here, a total of 9 channels, which is like 3x the improvement over the regular 2.4 gigahertz channels. Now these channels are non-interfering channels. They are so if you have an access point on channel 36 and you have an access point on channel 40, these are completely non-interfering. So we don't we get a much wider selection of channels on 5 gigahertz when it comes to channel width of 20 megahertz. But if you want, you can also use the DFS channels. Now I've dedicated a slide to DFS, and we'll understand what actually happens when you select the DFS channels. But if you do a site survey and you find out that you can use the DFS channels, even better. That gives us even more wide variety of channels to choose from, and that is widens your range of channels that the access point could be on. And if you have a floor with 30 access points, one access point could be on channel 36 and the other could be on channel, give me 1 second here. Now, with most of the devices actually even support the DFS channels. There are only a few devices out there which don't support DFS channels, but if you can use them, if you can use these DFS channels, it gives you a lot more channels to to select from. So here you have if we can use all of these Uni 2 and Uni 2 extended channels, it gives us we have 1, 2, 3, 4 here, 5, 6, 7, 8, 9, 10, 11, 12. So about 12 channels that we can still select from, which is still good enough. But if you look at 80 megahertz, that's just, you have Uni 1, just one channel, and Uni 3, just one channel. So now with our architecture where you have AP groups and you can select these channel widths per AP group, meaning where you know that you group these APs and these APs are going to be part of the same RF environment. And when let's say you do a deployment on a on a floor, work floor, and you have a lot more access points. You can put those group of access points on a 20 megahertz channel, and then versus if you have an auditorium, you can put them on an 80 megahertz channel if you want to. If you know that there are only a couple of access points covering that auditorium, we are going to still see a lot more clients come in. You can do that. So, but just keep in mind that this table is extremely important to understand as to how these channels, these are the non-interfering channels, and how the channel selection has to be done. Also, on 2.4 gigahertz, if you do not already know, you basically are restricted to only three channels, three non-interfering channels. You have channel 1, you have channel 6, and channel 11. That's it. In the US, you have these three channels that you use, and so you can space the access points accordingly. But it's extremely difficult to avoid co-channel interference in case of 2.4 gigahertz. That's how the channels have been allocated for 802.11 AC on the 5 gigahertz and N on the 5 gigahertz. It's very important to understand how these channels are spread out. So now that being said, let's go ahead and look at the radio settings again. So the bandwidth settings, so you have to be again prudent about what kind of bandwidth you select for the 5 gigahertz. For the most part, if you are doing, it's my recommendation that go with if you've selected DFS channels, then go with the 40 megahertz wide channel. But it's if you haven't done so, and it's always good to have a lower channel width, because channel width basically determines how much you can kind of pour in onto the channel, like how many devices. It's not how many devices, but it's like the analogy is it's a two-lane highway versus a four-lane highway. So now a lot more devices, a lot more data can be pumped in. But at the same time, you have to also look at the number of channels which are available to you. So it's always a trade-off between capacity and coverage. So just keep that in mind. Now the data rates, again, this is something that you can change here. So if you don't want your clients to experience, if you're in a highly dense environment, again, you have a lot more access points. I would turn off these basic data rates, or these, the 6 megabits, 9 megabits, 12 megabits. So you have at least a minimum of 18 megabits per second at data rate at which the clients connect to. Again, these settings that you see here are also applicable to each wireless LAN. So if you have a global setting here, and then each wireless LAN adopts the setting that you set here on the wireless LAN itself. So you can see here on the SSID, or not on the SSID, I should not say SSID, but wireless LAN, you have these data rate settings. So each wireless LAN can advertise the supported data rates, and these are advertised as part of the beacon messages that go out. So the clients are not even like, clients that are farther away from an access point won't even connect to it. So that's, those are the settings that are now also available to you on a per SSID basis. Then you go back here, And so you can be again, recommended is you disable these lower data rate values 6, 9, 12, if you know for sure that you have enough access points in a particular area. QoS. I'm going to talk about QoS and WMM in a companion video, which is going to be only focused on wireless QoS. But at a high level, we do support 802.11e, which is which was added in 2005. Um, and it allows for us to provide stations and access points to provide queues for like different queues for voice, video, background traffic, and your data traffic. So in that ways you can, it's like a wired equivalent of tags that go on the wired side, and now you have something similar on the wireless side. And again, we are going to talk about this in detail in a different video. 802.11h works in conjunction with TFS, and it's a channel switch announcement which is sent out to the channels once a radar is detected on a DFS channels. Once again, in a few minutes here, I will talk about what happens when what happens, or what is the whole idea of these DFS channels. So. Okay, so the next parameter is the 802.11n and AC, and these specify the MCS values for 802.11n, which is high throughput, and then very high throughput, which is 802.11 AC. These are the values which are supported. Uh, and if you're not familiar with the MCS, it's basically an index which provides you at what spatial stream, what modulation, what predictive data rate you're going to. It's basically a prediction of data rate that you would get based on how many spatial streams you're using, what kind of modulation is being used, and what the coding rate that is being used, and how much is the bandwidth, and whether you're using a short guard interval versus a long guard interval. Again, this is a table which is readily available, and you can see for let's say, I'll give you an example. If with the 802.11 AC, you can do 256 com modulation, and if you look at the very high throughput MCS index of 9 with three spatial streams and 256 com and 5/6 of the coding rate, and if I use 80 megahertz channel with a short guard interval, I can go up to 1.3 gigabits per second. But for for any station to achieve this value, you're expecting the station to be like at least like 10 to 15 or 30 feet away from the access point, like with a direct access to the with no loss of signal, direct access to the access. These are the ideal values. But essentially, an MCS index is something that gets negotiated based on how far the station is, from the access point, and then it adopts the data. If it it adopts these values based on how much signal it sees, RSSI values that it sees from the access point, and it gets these values from there. So again, something to keep in mind. You can download this table from the internet, and it will give you a good idea of what this is. So the MCS index values, again, you don't have to change from a configuration perspective. Nothing has to change from here. Everything that has been selected here is is enabled by default, so no changes here. All right, so RRM. Now, this is a topic where I'm going to spend a lot of time, and it's very important that we understand what radio resource management is. So, let's go ahead and dive a little deep into radio resource management. All right, so the whole idea of RRM, or radio resource management, is to produce a network with optimal capacity, performance, and reliability. Now, what does that mean? It means that now, in the absence of something, a feature like this, you will have to go into each access point. You'll have to basically do, a survey and find out, okay, I have three access points in this particular area. I have to put one access point on channel one, the other one on channel, 6, the other one on channel 11, and I have to manually put the power settings on the access point. Now this might be a good idea if it's an SMB and you know it's a very small office and it's fine, you know, you can do all that. But imagine a situation where you have hundreds of these access points in an enterprise kind of a setup. It's just not scalable. You cannot do that. So now so a feature like radio resource management is needed, which it's a very very complicated it's a very very complicated this feature uses a lot of algorithms, a lot of functions to come up with optimal coverage and optimal channel patterns for the access point, so that you avoid, you mitigate co-channel interference as much as you can. And you don't have to, as a network administrator, be out there monitoring and controlling each radio per se. So the RRM algorithms work separately on 802.11a, meaning the 5 gigahertz and the 2.5 and the 2.4 gigahertz radios. Uh, and they are enabled automatically. So some of the points that I've mentioned here, they are enabled automatically, but can be disabled by statically configuring the channels and power assignment. And you can, by default RRM is enabled, and if you want, you can to disable RRM per se, you go into each access point and you say, static channel is like channel 1, and then in that case that AP doesn't become part of RRM. We don't even, we just statically assign that. The RRM algorithms, they run at specified updated interval, which is about 600 seconds by default. And then, what it does is, so just to give you an example, if you look at this network over here, what actually happens is an access point sends an RRM neighbor message. All the neighboring access points receive that message, and based on how, what kind of power level they receive it at, what kind of noise that they sense when they receive that particular message, they send all that information. So this RRM neighbor message goes to this access point, which then in turn sends it to the controller. So controller receives these RRM messages from these different access points, and it in it uses these complex algorithms to figure out which APs are neighbors of each other, and builds like an access point neighboring table. So now at this point, the controller can make informed decisions as to which APs are part of the same RF environment, and then decide which, based on these different conditions, which access point can stay on its channel and which access point needs to change its channel, so that there is minimal co-channel interference, and how much power that they need to be transmitting at. So at a high level, if you look at the statement here, it's very important. It analyzes load, noise, interference. So load is, the act when those RRM neighbor messages go to the other access point, you can see that the access point knows on the other side how many stations are connected to the access point, what kind of traffic is coming on that access point. So it knows, what kind of load that access point is handling. The noise level, noise in is anything which is not in the RF environment, which is not 802.11n. So that's comprised, that becomes noise. And then the interference is, how much it is hearing from other APs, what it's hearing from the other APs which are also on the same channel. So if you have neighboring APs on the same channel, it that interference threshold goes up. Again, and then what it's hearing from the other AP. So all this information is analyzed, and then once the controller gets all this information, what it does is it does a dynamic channel assignment, meaning decides which access point goes on what channel. And the next is it does the dynamic power control, where it reduces a particular access point's channel. For the most part, transmit power control, we're going to talk about it in the next slide. It essentially reduces the power of an access point, so that there is minimal co-channel interference. and then it does coverage hole detection also, and this has got nothing to do with transmit power control or whatnot. This is a separate issue where it looks at a particular AP receiving or a particular area where you're seeing a lot more client failures and stuff, and it notifies the administrator that you have kind of a coverage hole in a particular area, and that needs to be addressed by either putting an access point over there, or or the APs itself increase the power level on that. So again, this is at a high level. You're using all the information from neighboring access points, building a neighboring table, and then performing radio resource monitoring, dynamic channel assignments based on what channels you select, and then doing coverage hole detection and correction. All right, so on the controller, if you come into RRM, you would see that this service is enabled by default. And then these are the different things that RRM does, right? It builds that neighbor table. By the way, you can actually look at what the access points, what kind of neighbors the access point sees itself. So what other access points it can hear right here. So if you do it, if you go to monitor access points all APs, if I look at this access point which says Dolphins 1, you can come here. Okay, oh, it's in radios, sorry. So you go into radios 802.11.1 AC, you go in 802.11 ABGN. You can see that for Dolphins 1, it sees two neighboring APs, and it can hear these two neighboring APs, and the neighboring AP is at channel 165, and then this one is further away from our kid, and both of them are transmitting at 20 dBm, and this is the RSSI that it hears from the neighboring APs. So that neighboring AP table is known to each access point because of those RRM neighbor messages. You can come here to radio 802.11 AC RRM. Again, so radio resource management, we're going to talk about dynamic transmit power control later on, but the first thing, let's talk about dynamic channel selection. So once you've built that neighbor table, you're going to do this is the interval in which it does the algorithm, runs the algorithm based on all the information that is received from those RRM neighbor messages from different access points. This is the threshold value that you set, that if you actually hear that the channel utilization threshold is gone above 80%, then you need to make a dynamic channel selection, or whether the interference level is also above 80%. So if you are, that means that two APs are definitely right next to each other on the same channel. You want to make sure that a channel change is done at that point. Now, delayed channel change is where when you are doing this kind of, when you are running this algorithm and you determine that which AP stays on the same channel and the other AP has to change the channel. When you select this, you don't make the channel switch right away. You make the channel switch. If you make the channel switch right away, if it's a working environment, there could be an issue where stations are disconnected because you're changing the channel. So you are very careful about that. So you can select this option, delayed channel change, and at that time it will make that channel, or it will run the algorithm again at 4 in the morning, and stop at, like, and then keep doing this every 120 seconds, and then end eventually at 5 a.m., and then make the channel switch. And the channels that it would select from would be these channels. So in by default, if you see, channels 36, 40, 44, 48, 149. So Uni 1 and Uni 3 channels are selected. The remaining DFS channels are something that you have to, if you can use it in the environment, nothing like it. It's nothing like it. Those are the channels that will be selected, and that way you can spread the channels across multiple access points, and your chances of co-channel interference even reduces further. So those are the parameters that you need to understand. Now, for the most part, the default values are good. You too should not have to come in and change it, but it's always good to know what these values actually mean. All right, so now let's talk about dynamic transmit power control. So in case of dynamic transmit power control, the controller dynamically controls the access point transmit power based on the real-time wireless LAN conditions. So again, these are the messages that are sent back to the controller, and the controller basically adjusts the power level based on what it hears, what kind of RF environment a particular access point may be. Now, typically, the power is kept low. It normally always decreases the power. You would never see it increase the power unless it's doing some sort of a correction on coverage hole detection, which we will talk in the next slide. But, so typically it increases and decreases, but for the most part, it decreases the power to reduce the interference. But in case of an like given an example here, if an access point fails or becomes disabled, and we know it at the back end, if we lose the cap map connection, that an access point has failed, and we now have the neighboring APs in that, they just go about increasing the power level so that you cover you don't there's no coverage hole in that particular area. Now, again, the coverage hole detection feature is completely different, where it is actually looking at the conditions, of a particular RF environment where there are a lot of clients where they are reporting a lot of failures, and there's a lot more parameters to it. It just provides enough RF power to achieve desired coverage levels while avoiding channel interference between the access points. The whole idea of doing this is you don't, once you've determined who your neighbors are, once you determine what the RF conditions are, you adjust the power at such a level that there is minimum co-channel interference. So that's dynamic transmit power control. So if you look at the settings that we have, is the idea is to make sure that the access points, the target RSSI for each access point should be next 70. Now there are a lot of APs that need to be part of this to do this. So if you have just like about two or three APs, for the most part, this operation doesn't work. It requires more than three access points, or more than three neighbors for it to trigger dynamic power control. So if you have like a two or three access points near or a neighbors, then it might keep all the access points at maximum power. But however, if you have more than three access points as neighbors, that's where this thing triggers, and then it selects between 16, or in my case I've kept it 16, but you have to keep it lower. But default settings are far lower than this. And then you can select how much maximum you can go up to if an access point has gone down, for that matter. So these are the settings for the deep dynamic transmit power control. Let's talk about coverage hole detection. Right, so let's talk about coverage hole detection. So again, what we've talked so far is the RRM neighbor messages that come to the controller trigger either a transmit, power control, and then there's another feature called this coverage hole detection, where again, using these values that the controller receives, it is able to notify you of an environment of like a structural issue, where you may say that based on certain parameters or based on certain configuration, what I'm hearing from different clients, I think there might be a coverage issue because some of these clients are not moving over to the next access point. So our RRM coverage node detection algorithm detects areas of radio coverage in a wireless LAN that are below the level needed for robust radio performance. That's what it means. Again, it alerts you of a need for an additional AP, and if the clients and access points are detected at threshold level, so we look at RSSI of the client on a particular access point. what's the failed client count, the percentage of failed packets, the percentage of failed clients, and if they are lower than those specified, then the access point sends a coverage hold alert to the controller. So we know that there is a particular area which needs to be looked at. Now the alert indicates, again, as I say here, the alert indicates the existence of an area where clients are continually experiencing poor signal coverage without having a viable access point to roam to. Now the controller discriminates between the coverage holes that can and cannot be corrected. So for the coverage holes that can be corrected, the controller mitigates the coverage hole by increasing the transmit power level for those specific access points. So for the most part, uh, if you go here, the dynamic power control feature typically reduces the power of the access point, and it's meant to kind of reduce the power so that there's minimum co-channel interference. But in the case of coverage hole detection, if something is detected like that where it's experiencing a lot, so it may try to mitigate it by increasing the power level of the access point so that it can provide coverage in that particular area. But it not necessarily fixes it. So you have to be very careful that increasing that power level, because it can also increase co-channel interference. So it's a very difficult algorithm that you run behind the scenes to make sure that the environment is well taken care of. So if you look at the parameters here, for coverage hole, we obviously have to keep the feature enabled. You want to keep a trap warning, so that goes to your management platform. And we are going to dedicate a video to WEM where this kind of information is sent. And as I mentioned, these are the parameters that are configured. So you can say 25% of failed client count, and then the minimum RSSI that it receives for voice. So if it's seeing a lot of stations that are doing voice, I want the minimum RSSI threshold for these to be minus 78. If they are, if I have a lot of stations on voice or using voice, and they are kind of at a RSSI value which is more than next 78, then I should trigger the algorithm to make sure that there's no coverage hole, and if I want to increase the power level or whatnot. Similarly, for data traffic, you want to keep it at neg 85, but you also want to look at the field client. How many clients are reporting something like this? So you don't want to take an action on this based on just one or two clients reporting that this kind of issue, because you may have a sticky client in your environment which is not making a roaming decision pretty quickly. But if you have a lot of these clients in your environment which are doing this, then you know that you need to do something about it. And again, you wait for an interval of 120 seconds before you actually make a decision to do anything about it, because it could be a failed client count could be because of a lot of interference which would be temporary in that area, or it could be other factors, but so you wait to make sure that there is something going on before you actually make that kind of decision. So those are the actual settings that you have for coverage hole detection. That's on a global level. We've already looked at the radio settings on the per in the SSID level, and again, it's very important to keep in mind, what kind of data rates you want to keep enabled. It's always good to turn off lower data rates so that the end user experience is better. You don't even allow anybody with connecting at a lower data rate at a farther distance to connect to the access point. So it's always good to disable these low data rates on both 5 and 2.4 gigahertz in a high density environment that you have a lot of radios. Again, going back to the AP groups, you can see, as I mentioned, each AP groups, you can come in here and you can change the RF parameters. There are a few parameters that you can change. You can basically say the bandwidth is certain megahertz, And you can also change the max allowed stations on an AP. So on per radio, we support up to 127 clients. But if you're in a classroom kind of environment where you want to restrict number of devices that connect to the access point, you can change this value to about 30. So per radio, I don't want to hear more than, or I don't want to connect more than 30 devices. I want to restrict that to 30 devices so that everybody is able to use a different application. So that's something that is allowed, that's also available to you to choose from either the global parameters or the group parameters. So, if you want to, at any particular point, you want to change, let's say you have an access point in an area and you want to increase the power level and fix the channel level on that access point. So you would come into the AP itself, go into the radio setting, and you would change the channel, and you'd say channel fix and change the channel from 165 to whatever it is, and then you can also increase the power at this and the power levels can only be increased. Those are all specified by the FCC. They're regulated by the FCC, so how much power you can transmit on each channel is regulated in every country. So you can change that, make that decision right here. And once you do that, if you come to the monitor access point radio, this is where you actually see what radio a particular access point has been put on. So you can see these have been dynamically allocated. Anything without a star has been dynamically allocated to the access point. Anything with a star, if there is a star sign here, that means it's a anything with a star is statically assigned channel or power level, but these seem to be assigned by the RRM. So again, you can see per radio how many devices are connected. It's pretty good information right here. If we click on the AP itself, it gives you again detailed information about the statistics. You can see radio input. Anything that is fixed is with a star. So, what kind of air quality is it experiencing, on the 5 gigahertz channel? What's the channel utilization? So it's pretty good information right here. And then again, what neighboring access points are, what is, how far it can hear them, how far away from, what's the RSSI level that it hears these access points at. And these are all exchanged by the RRM neighbor messages. So again, quite a lot of information right here to look at. So that's all that I had. I'm trying to see if I missed anything here. On the RRM side, those are the parameters, and this is how these parameters work. So again, when you're selecting the channels, make sure that you can use these DFS channels, and if you can, it's nothing better than that. Another thing I want to talk about is some of these advanced features right here. So let's talk about sub-channel groups. The sub-channel groups is where you can at a global level specify all those channels, the dynamic channels that we talk about. But with a sub-channel group, if you identify that a particular RF environment is seeing a lot of interference, in a particular area, and I want to make sure that I stay away from certain channels when I'm doing the dynamic channel selection, I can create a sub-channel group here, and I can say that, let's say if I'm in an environment where I know channel 149 there's something, based on my spectrum analysis, there's something going on channel 149. I don't want to use channel 149. I do not select that, and I then turn around and select the access points in only those channels. Now, when would this be useful? So assume that you have a controller which is serving multiple sites, and certain sites you want to use channels 149 through channel 165, and certain sites you know that channel 149 is going to be crowded, or there's going to be something going on there. So you can create at a global level, you can keep dynamic channel selection for channel 149, but you can now create a sub channel group, put the APs in that particular branch office where channel 149 is crowded, into this subchannel group and uncheck channel 149, so that for that group of access points I don't select channel 149. So this again, it's giving you something which is a very flexible architecture wise. Energy saving is another concept where I've seen specifically in education, a lot of schools want you to turn off the radios. This is again a green initiative where you turn the radios off on the weekend. So you can come here, create a group, and specify, the APC threshold values, and you can say unconditional radio off, and you can specify the time of the day or the weekend, and you can specify, which APs you want to select to turn the radios off in that particular area. And APC threshold is, if you say, if the access point controller sees like less than 10 stations or 10 stations, you want to turn the radio off. Because in those 10 stations, that's probably over the weekend, you have very few stations in which are connecting to the access point controller. So you can put this value here. But you can, for the most part, you might be able to use this unconditional radio off for the weekend and turn it off, and you can say start hour and end hour, and then after that the radios turn on automatically. So those are the settings I wanted to talk about as far as radio goes. I will talk about wireless QoS in another set of another video, and at that time we will talk about WMM and 802.11e and how that works. But before I forget, let me talk about the DFS channels. I completely forgot about that. So what happens when a DFS enabled radios, it detects a radar in the neighborhood. So if it actually finds a radar, what process it goes through. So first thing that it does is starts blocking the new transmissions on that channel. It flushes the power save client queues. It broadcasts this 802.11 edge channel switch announcement that we talked about. Disassociates all the remaining channel, and then it randomly selects a DFS channel. So if it selects if it doesn't select a DFS channel, then it enables the beacons and accepts the client associations right away. But if it turns around and selects a DFS channel, it will scan the new channel for radar signals for about 60 seconds. And then if no radar is detected on the new channel, the wireless device enables the beacons and starts accepting the client associations. Again, if the signal is detected, it turns around and selects a new channel. That's something to keep in mind. That's why DFS channels, you have to be very, very careful when you select these DFS channels. You have to be extremely careful that there's no radar in the neighborhood that's being used, because the moment it detects a radar or signature, and the our access points have these dedicated sensor modules. So we do these sensing. We sense the air, scan the channels continuously, and the moment we detect something, we switch the channel, and that's actually not a good thing, because now you are essentially disturbing the setup for your connected clients. The clients are already connected to the access point, and you're kind of switching channels, and that disconnects that those clients. So it's not a good thing. So you have to be very careful when you select the DFS channels. All right, so that's all that I have in this video. We will talk about some more advanced features in the next video. Thank you so much.